All right, we're going to start to look at linear relationships in tables as we start to get into things like constant rate of change and different things like that. So first, let's go ahead and fill out our fill in the blank up here. So we have linear relationship is a relationship between two variables that create a straight line when graphed. So hopefully you noticed I made this kind of funny. The line part of linear is bold or capitalized because line, linear, I'm hoping we make that connection. So if I hear linear relationship, I should automatically know that it's going to be a straight line when graphed, which just means that it's either growing, it has a constant rate of change going up or down. It's changing by the same amount each time. So this relationship going up or down at a constant rate of change, this means that the change from one term to the next is the same. So where might we see this type of relationship in the real world? Well, we can see it all over the place. We can see time. Time is always increasing by the same amount, and we're ignoring, black holes and different things like that we know that can affect time. Purchasing the same type of items, again, ignoring anything to do with, say, discounts or coupons. But if I purchase one pencil for 10 cents and I purchase two pencils, then I'm assuming they're both 10 cents and it's going to be 20 cents. If I purchase a third pencil, it'll be 30 cents. So it's going up by the same amount each time. Or maybe age, that could be another one that has to do a little bit there with time, right? So you're always aging at the same constant rate and driving at a certain speed. So you need to make sure you're going the exact same speed the whole time, but then your distance is going to be based on how long you've been driving, because you'll go the same number of miles every hour that you're driving as long as your speed stays the same. That's just a couple things that I'm throwing out there that we would see this type of relationship in the real world. So now what we're going to do is when we're given a table, we're just going to evaluate what are the changes in the X row, or what are the numbers in the X row changing by each time. So we want to know, what are they changing by? When I jump from 9 to 11, well, that went up by 2. 11 to 13, that went up by 2. So the rate of change for X is 2. So what are the changes in the Y row? So we have this Y row here. So now I'm going to go 54 to 66, that's 12. And then 66 to 78, well, that's another 12. So I'm going up by 12 each time here. So now I know what the change in the X's are and the change in the Y's are, so I can write what my constant rate of change is. And when we do this, I have a little note down here, when writing the ratio for rate of change, Y goes over X. And we haven't fully started this yet, but we can review it just a little bit here out loud. This has to do with specifically slope, because we're looking at rise over run when we're looking at a graph. So Y goes over X, just like this. So Y is going to be 12, X is going to be 2, and then you want to make sure you reduce that because 12 and 2 can reduce. So I can divide both of these by 2. 12 divided by 2 is 6, 2 divided by 2 is 1. So a 6 over 1 would be the constant rate of change, which we could actually just write as 6. We wouldn't need the over 1 part. All right, let's go ahead and take a look at a couple more tables just so that we can see how these work and how Alex is going to expect us to answer these questions. So in table number 1, we have and 2, we have an X column and a Y column. I don't know why this one came out so much bigger. Kind of looks a little funny. So we want to look at that same idea. What is X changing by each time? And this one is pretty easy. 1, 2, 3, 4. So each time is changing by 1. Right? I'm going up by 1 each and every time. And for the Y column, I want to do the same thing. Am I going up by the same amount? This is what we're testing. So if we don't have the same amount, so now I went up by 10, but then I'm going up by 12 from 18 to 30, and I'm going up by 14 from 30 to 44. So it's constant on the X's, but it's not constant on the Y's. So this is an example of not proportional. I can't actually write one fraction for each one, because if I wrote this one, it would be 10 over 1, the next one would be 12 over 1, the next one would be 14 over 1. Well, those don't equal each other. 12 over 1 and 10 over 1 and 14 over 1 are completely different ratios. So this is not proportional because Y is not constant. All right, so let's look at table number 2. So now we're going to do the same thing. We're going to say what's the change in the Y's. So from 5 to 8 is 3. From 8 to 11 is 3 again. So that's constant. It's going up by 3 each time. Now with the y's, I'm going up. From 10 to 16, it's 6. From 16 to 22, it is 6. So yay! We found a constant rate of change. So remember, it's going to go 6 over 3, y over x, and then I want to reduce. So it's going to be divide by 3, because both of these can divide by 3. So 6 divided by 3 is 2. 3 divided by 3 is 1. So they are proportional because we see that they're the same. That's what we're looking for proportional. They're constant. So they are proportional. And y is blank times x. Well, y is on top, x is in the bottom, so y is 2 times x. It's 2 times as big. Because y is 2 and x is 1, so y is twice the size. So that's how they want you to fill it out. Alright, so that was looking at a linear relationship in a table. I hope that helped, and I will see you in the next video.